March 3rd, 1943. 1,427 hours. Anti-Aircraft Operations Room, 1st British Corps Headquarters, Beaune, Algeria. Major General Frederick Pyle stood motionless before the plotting table as American technicians calibrated equipment that looked nothing like the British radar sets he'd commanded for 3 years. The cathode ray tube displayed a single bright dot tracking across the screen with mechanical precision. 72 miles away, a lone P-38 Lightning was executing test maneuvers over the Mediterranean. What made Pyle's hands grip the table edge was not the detection itself, but what the Americans claimed their system could do next. Fire control solutions calculated automatically, continuous tracking through jamming and chaff, accuracy sufficient to guide shells within lethal radius without visual contact. For 40 months, British anti-aircraft doctrine had accepted that radar could detect aircraft but could not track them accurately enough for blind firing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematics of ballistics, combined with the limitations of existing radar technology, meant that gunners still required visual confirmation before engaging targets with any hope of success. Now, in a requisitioned warehouse on the North African coast, American engineers from the MIT Radiation Laboratory were demonstrating technology that rendered those limitations obsolete. The SCR 584 radar, weighing 4 tons and mounted on a trailer that could be towed by a standard truck, was tracking that distant fighter with accuracy measured in fractions of a degree. The system's analog computer was calculating firing solutions faster than the best-trained gun crews could plot them manually. What no Luftwaffe pilot yet understood was that the electromagnetic spectrum had become a killing ground, where darkness, clouds, and evasive maneuvers provided no sanctuary. The German Air Force, which had perfected low-level attack tactics and night interdiction based on the assumption that anti-aircraft fire required visual contact, was about to encounter weapons that could see through weather, smoke, and midnight darkness with perfect clarity. The mathematics of air defense were being rewritten not in trajectories lost or missions failed, but in the sudden obsolescence of tactical doctrines built on one fundamental assumption, that aircraft invisible to gunners were safe from anti-aircraft fire. The evolution of radar-directed anti-aircraft fire had been frustrated by technical limitations that seemed insurmountable through 1942. British Anti-Aircraft Command, established in 1938 under General Pyle's leadership, had deployed thousands of heavy and light anti-aircraft guns around British cities and military installations. These guns, primarily 3.7-inch and 4.5-inch heavy weapons, could throw shells to altitudes exceeding 30,000 feet. But hitting a maneuvering aircraft at such distances required precise knowledge of the target's position, course, speed, and altitude. Early British radar sets, including the chain home system that had proven decisive during the Battle of Britain, could detect aircraft at long ranges, but lacked the precision necessary for gun laying. The radar would provide general bearing and approximate distance, but the accuracy was measured in hundreds of yards. For searchlight direction, this was adequate. For anti-aircraft gunnery, it was nearly useless. The gun-laying Mark I radar, introduced in 1940, represented Britain's first attempt at fire control radar. Operating at 50 centimeters wavelength, it could track aircraft to approximately 20,000 yards with accuracy of roughly plus or minus 40 yards in range and plus or minus 1 degree in bearing. While a significant improvement over previous systems, this accuracy remained insufficient for effective blind firing. Gun crews still required visual contact or searchlight illumination to achieve acceptable hit rates. During the Blitz of 1940 to 1941, British anti-aircraft guns fired approximately 20,000 shells for every German aircraft destroyed. Most of these shells were fired with visual aiming or searchlight tracking. Radar provided early warning and approximate positioning, but the final engagement remained dependent on human observers seeing the target. The Germans faced similar limitations. Their Würzburg radar, introduced in 1940, operated at 53 centimeters wavelength and provided reasonably accurate tracking for a single target. The system could track aircraft to approximately 40 kilometers with accuracy better than British gun-laying Mark I. However, it could only track one target at a time, making it vulnerable to saturation tactics, and it required separate radars for search and tracking functions. Freya radar handled long-range detection, while Würzburg provided tracking data for guns or night fighters. The flak divisions defending German cities deployed hundreds of 88mm and 105mm guns, coordinated by complex command systems. But like their British counterparts, German gunners achieved low hit rates when firing without visual contact. The standard doctrine accepted that radar could direct searchlights or bring fighters near targets, but could not provide firing solutions accurate enough for unguided anti-aircraft shells. The technical challenges seemed fundamental. Radar accuracy depended on wavelength, antenna size, and signal processing. Shorter wavelengths provided better resolution but required more sophisticated components. Larger antennas improved directional accuracy but created mechanical complexity. Most critically, tracking a moving target required continuous updates while simultaneously calculating where that target would be when shells arrived seconds or minutes later. This ballistic prediction problem had been addressed through mechanical computers, but these devices were slow, cumbersome, and required constant manual input. The British Kerrison predictor, introduced in 1942, could calculate firing solutions for fast-moving targets, but it still depended on accurate position data that existing radar could not reliably provide. American entry into the war brought different technical approaches and institutional structures. The National Defense Research Committee, established in June 1940, coordinated civilian scientific contribution to military technology. Within this organization, Division 14 focused specifically on fire control, bringing together physicists, engineers, and mathematicians from universities and industry. The MIT Radiation Laboratory, which had revolutionized naval radar with the cavity magnetron-based systems, turned its attention to anti-aircraft fire control in 1941. The laboratory's researchers understood that effective radar-directed anti-aircraft fire required three integrated capabilities: precise tracking of target position in 3 dimensions, accurate prediction of future target position, and automatic data transmission to gun mounts. Dr. Ivan Getting, who joined the Radiation Laboratory in 1941 after completing his doctorate at Oxford, led the team developing what would become the SCR 584. Getting's background in physics and astronomy provided crucial insight into the tracking problem. He recognized that anti-aircraft fire control was fundamentally similar to astronomical observation. Both required tracking moving objects with extreme precision and predicting their future positions based on current data. The SCR 584 project began in late 1941 with specific performance requirements. The system must track aircraft automatically without manual intervention. It must maintain track through evasive maneuvers and jamming. It must provide accuracy sufficient for blind firing with acceptable hit probability. It must be mobile enough for field deployment, and it must be manufacturable in quantity with 1940s technology. These requirements demanded innovations across multiple domains. The radar itself would operate at 10 cm wavelength, using cavity magnetron technology for microwave power generation. This shorter wavelength, compared to British and German systems operating at 50 centimeters, would provide superior resolution. The antenna would use a parabolic dish approximately 6 feet in diameter, providing narrow beam width for precise angle measurement. The system would employ automatic tracking, using error signals generated by comparing the target's position to the antenna pointing direction to drive motors that kept the antenna aimed at the target continuously. An analog computer would calculate ballistic solutions based on the continuous stream of position data, and the entire system would mount on a single trailer, making it transportable and deployable with frontline forces. The technical challenges were formidable. Automatic tracking required servo mechanisms more sophisticated than anything previously used in military equipment. The analog computer had to perform complex calculations in real time, updating firing solutions multiple times per second. The microwave components had to function reliably under field conditions, including temperature extremes, vibration, and dust. Most critically, every component had to work together as an integrated system, where failure of any single element would disable the entire capability. The first prototype, SCR 584, underwent testing at Camp Evans, New Jersey, in mid-1942. Initial results were promising but revealed numerous technical problems. The automatic tracking occasionally lost targets during sharp maneuvers. The servo motors generated electrical noise that interfered with the sensitive receiver. The analog computer produced erratic solutions when tracking crossing targets. Each problem required careful analysis and engineering solutions. By late 1942, after multiple iterations and improvements, the SCR 584 achieved performance that exceeded all design requirements. The system could detect aircraft at ranges approaching 90 miles under optimal conditions. It could automatically acquire and track targets at ranges exceeding 50 miles. The tracking accuracy was approximately plus or minus 50 yards in range and plus or minus quarter degree in bearing. The analog computer, designated the M9 gun director, calculated firing solutions with sufficient accuracy that shells could be guided to within lethal radius of targets the gun crew never saw. The M9 gun director represented a revolution in analog computing. Designed by Bell Telephone Laboratories under Dr. David Parkinson, the device used mechanical gears, cams, and electrical servos to solve differential equations describing projectile motion. It accepted inputs from the SCR 584 radar, including target range, azimuth, elevation, and velocity in 3 dimensions. It calculated the point in space where the target would be when shells arrived, accounting for projectile ballistics, wind, air density, and gun characteristics. The solutions updated continuously, 30 times per second, providing smooth tracking even during violent evasive maneuvers. The mechanical complexity was extraordinary. The M9 contained approximately 2,000 gears and numerous servo motors, all synchronized to perform calculations that would have required several minutes using manual methods. The device could track targets moving at speeds exceeding 400 miles per hour, calculating firing solutions for guns located up to 1,000 yards from the radar itself. Integration of the SCR 584 radar with the M9 director and standard anti-aircraft guns created a complete fire control system designated the SCR 584 M9 combination. This system represented the most advanced anti-aircraft capability in the world, exceeding German and British systems by a generation of technology. Production began in early 1943, with Western Electric as the primary contractor. The manufacturing challenge was substantial. Each SCR 584 required precision machining for the antenna mount, careful assembly of sensitive microwave components, and extensive testing to verify performance. The M9 directors required equally precise manufacturing for the mechanical computers. Despite these challenges, American industry delivered the systems in quantity. By mid-1943, production had reached approximately 50 units per month. By the end of the war, over 1,400 SCR 584 systems had been manufactured. The first combat deployment of the SCR 584 occurred in North Africa during the spring of 1943. American and British forces, having secured Algeria and Tunisia, faced continuing Luftwaffe attacks against ports, airfields, and troop concentrations. German aircraft, operating from bases in Sicily and Italy, could strike North African targets and return before Allied fighters could intercept them effectively. The attacks typically occurred at dawn or dusk when low sun angles made visual aircraft spotting difficult. Luftwaffe pilots had learned to approach at low altitude, using terrain masking and timing to avoid radar detection until the final attack run. Once over target, they would climb rapidly, release bombs, and dive away before anti-aircraft fire could be effectively directed. The tactic exploited the limitations of existing Allied radar and fire control systems. Traditional anti-aircraft doctrine required visual contact or searchlight illumination for accurate fire. By the time guns could be brought to bear on visually acquired targets, the aircraft were often completing their attack and beginning evasive maneuvers. Hit rates remained discouragingly low, typically requiring several hundred rounds of heavy anti-aircraft ammunition to achieve a single kill. The SCR 584 systems, deployed to North Africa in March 1943, changed this equation fundamentally. Battery commanders who had spent years directing visual anti-aircraft fire were initially skeptical of the American claims. Blind firing went against every principle of gunnery they had learned. The idea that radar and mechanical computers could solve problems that required experienced human judgment seemed implausible. The demonstration for General Pyle on March 3 was intended to overcome this skepticism by showing what the system could actually achieve. The P-38 Lightning had been instructed to execute a series of maneuvers that would challenge any tracking system. Steep climbs and dives, sharp turns at various altitudes, rapid changes in speed and heading. These maneuvers represented the most difficult tracking scenarios gunners would encounter in combat. The SCR 584 acquired the Lightning automatically at 72 miles range. The operator had simply pointed the antenna in the general direction based on radio communication with the aircraft and pressed the automatic tracking button. The system had searched its assigned sector, detected the largest return, and locked onto it without further human intervention. On the plotting table, the track was displayed with geometric precision. As the Lightning maneuvered, executing tight turns and rapid altitude changes, the radar track remained smooth and continuous. The M9 director continuously calculated where the aircraft would be if shells were fired. A separate display showed the predicted impact point, updating smoothly as the aircraft maneuvered. The accuracy was measured in feet at ranges exceeding 10 miles. General Pyle watched the demonstration with the careful attention of a man whose professional judgment was being challenged. He had commanded anti-aircraft defenses through the Blitz, the V-1 flying bomb campaign, and countless Luftwaffe raids. He understood the limitations of existing systems intimately. What he was witnessing seemed to violate those limitations completely. When the demonstration concluded, Pyle requested a meeting with the American technical staff. His questions revealed both professional competence and healthy skepticism. How did the system perform in rain or snow? What happened if the target deployed chaff or other countermeasures? Could the radar distinguish between friendly and enemy aircraft? How many targets could be engaged simultaneously? The American engineers provided detailed answers based on extensive testing. The 10-centimeter wavelength was affected by heavy precipitation, but remained functional in conditions that would blind visual observers completely. Chaff presented challenges, but the system could track through moderate chaff clouds by focusing on the strongest return. The radar itself could not distinguish friendly from enemy aircraft. That remained an identification problem requiring other solutions. And each SCR 584 could track only one target at a time, though multiple radars could operate in proximity without mutual interference. These limitations were real but manageable. The critical capability, blind firing with accuracy sufficient to achieve acceptable hit rates, had been conclusively demonstrated. Pyle authorized immediate deployment of SCR 584 systems to British anti-aircraft batteries defending critical targets in North Africa. The first combat engagement would come within weeks, and it would demonstrate the system's capabilities in a manner no demonstration could match. April 11, 1943, 1,847 hours. Anti-aircraft battery position, Bone Harbour, Algeria. The alert had come through at 1,832 hours. Hostile aircraft approaching from the north, bearing 320, range approximately 40 miles. The Luftwaffe was mounting another dusk raid against the crowded harbour, where American and British supply ships were unloading equipment for the final offensive against Axis forces in Tunisia. The SCR 584 radar, operated by a crew from the US. Army's 90th Coast Artillery Battalion had been tracking the incoming formation for several minutes. 6 aircraft flying in loose formation at 12,000 feet, heading directly for Bone. The identification was not certain. The radar could not determine if these were German bombers or Allied aircraft on final approach to nearby airfields. But the bearing and altitude were wrong for friendly traffic, and the formation was maintaining attack spacing. At 1,845 hours, Royal Observer Corps spotters confirmed visual identification, 6 Junkers Ju-88 medium bombers, approaching through scattered clouds that would make visual tracking difficult. The SCR 584 operator had already locked onto the lead aircraft. The M9 director was calculating firing solutions for the battery's 4 90mm guns, positioned 300 yards from the radar trailer. The battery commander, a British captain who had fought through the Blitz, made his decision. Commence firing, predicted barrage. The guns began firing at 1,846 hours, when the German formation was still 10 miles from the harbour. The shells were directed not at where the aircraft were, but at where the M9 predicted they would be when the shells arrived. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The gun crews could not see their targets. They were firing based entirely on data transmitted electrically from the radar and director. The first salvo burst in the empty sky. The second salvo, adjusted automatically by the M9 as it refined its tracking solution, burst closer. The third salvo detonated directly in the path of the lead Ju-88. The bomber staggered as shrapnel tore through its port wing and fuselage. It fell away from the formation, trailing smoke, attempting to turn back towards Sicily. It would crash into the Mediterranean 6 miles offshore, taking its entire crew down with it. The remaining 5 bombers scattered, breaking formation and initiating evasive maneuvers, but the SCR 584 maintained track on a second aircraft, and the M9 continuously updated firing solutions as the bomber jinked and turned. The guns continued firing in predicted barrages, throwing shells into the sky ahead of the evading bomber. At 1,851 hours, a direct hit destroyed the second Ju-88, which exploded in mid-air with such violence that debris was later found scattered across a quarter-mile radius. The surviving 4 bombers jettisoned their bombs harmlessly into the sea and fled north at maximum speed, staying low and initiating radical evasive maneuvers. They had achieved nothing, lost 2 aircraft and 14 men, and never delivered a single bomb near their intended target. The battery had fired 72 rounds of 90mm ammunition, achieving 2 kills. This represented a hit rate more than 10 times better than the historical average for anti-aircraft fire. More significantly, both kills had been achieved through blind firing. The gun crews had not seen the targets they destroyed. The engagement had occurred at ranges where visual fire control would have been impossible. The Luftwaffe pilots had been shot down by weapons that seemed to anticipate their evasive maneuvers, placing shells precisely where the aircraft would be rather than where they had been. News of the engagement spread rapidly through Luftwaffe intelligence channels. German pilots had encountered accurate anti-aircraft fire before. Visual ranging and experienced gun crews could achieve impressive results under ideal conditions. But this engagement had occurred at dusk, through scattered clouds, at ranges exceeding 6 miles. The accuracy seemed impossible unless the Allies possessed some new form of fire control radar operating at wavelengths German systems could not match. The implications were analyzed at Luftwaffe headquarters in Rome. If the Americans had deployed radar-directed anti-aircraft systems that could achieve blind firing with such accuracy, then the tactical assumptions underlying German air operations would need fundamental revision. Low-level approach and high-speed attack tactics had been developed specifically to minimize exposure to anti-aircraft fire by reducing the time gunners had for visual tracking. If guns could now track and engage targets without visual contact, these tactics might no longer provide adequate protection. German signals intelligence, responsible for monitoring Allied radar and electronic emissions, began searching for evidence of new fire control systems. The Luftwaffe's Signals Intelligence Service, operating under General Wolfgang Martini, maintained extensive records of Allied radar frequencies and characteristics. By mid-1943, they had catalogued most British and American radar systems operating in the Mediterranean theatre. But the search for this new fire control radar would prove frustrating. The SCR 584 operated at 3 to 1000 MHz, in the microwave region that German receiver equipment could barely detect. More critically, The system used frequency modulation and sophisticated signal processing that made it difficult to characterize even when detected. German listening posts occasionally registered brief pulses of microwave energy during Allied anti-aircraft engagements, but the signals were too brief and too infrequent to analyze properly. The Würzburg operators who manned German fire control radars understood their equipment's limitations. Their systems operated at approximately 5 to 160 MHz, providing good tracking accuracy for single targets, but requiring careful manual operation. The idea that the Allies had deployed automatic tracking radars with superior accuracy challenged German assumptions about technological leadership in radar development. German radar development had been pioneering in the 1930s. The Freya and Würzburg systems represented sophisticated engineering when introduced in 1938 and 1940, but German development had stagnated, relatively after initial deployments, focusing on incremental improvements rather than revolutionary advances. The cavity magnetron technology that enabled Allied microwave radar had been beyond German manufacturing capabilities throughout the war. By May 1943, SCR 584 systems were deployed at multiple locations across North Africa. The batteries defending Algiers, Beaune, Bizerte, and Tunis all received the new radar-directed fire control systems. Luftwaffe raids against these ports, previously conducted with reasonable expectation of survival, became increasingly hazardous as the radar-directed guns achieved kill rates that German planners had considered impossible. The statistical evidence mounted through late spring and summer 1943, anti-aircraft batteries equipped with SCR 584 achieved hit rates averaging 1 kill per 100 rounds fired, compared to historical averages exceeding 2,000 rounds per kill for visual firing. More significantly, the radar-equipped batteries achieved kills at ranges and in conditions where visual firing was completely ineffective. Night attacks, previously the safest time for Luftwaffe operations, became killing grounds. The SCR 584 tracked aircraft through complete darkness, with the same accuracy it achieved in daylight. German pilots discovered that darkness provided no sanctuary when gunners could see electromagnetically rather than visually. Evasive maneuvers that should have broken visual tracking had no effect on radar lock. The psychological impact on Luftwaffe aircrews was profound. Pilots described the uncanny accuracy of anti-aircraft fire that seemed to anticipate their maneuvers. Shell bursts appeared ahead of their aircraft as they turned, as if the gunners knew where they would be before they got there. The traditional doctrine of flying through the barrage, accepting some losses but completing the mission, became unsustainable when barrage accuracy increased by an order of magnitude. Attack profiles had to be modified. The standard approach at medium altitude, 12 to 15,000 feet, brought aircraft into the optimal engagement envelope for radar-directed guns. Pilots began either staying very low, below 1,000 feet where radar tracking was degraded by ground clutter, or flying very high, above 25,000 feet, where ballistic calculations became less accurate and projectile effectiveness decreased. Both alternatives carried their own risks. Low-level attack required penetrating increasingly sophisticated Allied fighter coverage and exposed aircraft to light anti-aircraft weapons. High-altitude attack reduced bombing accuracy and increased exposure time over the target. The Luftwaffe was being forced into tactical compromises that reduced operational effectiveness regardless of which approach they chose. The Sicily invasion in July 1943 provided the most comprehensive demonstration of SCR 584 capabilities. The Allies deployed dozens of radar-directed anti-aircraft batteries to protect the invasion fleet and beachheads. German and Italian aircraft attempting to attack the landing forces encountered defensive fire unlike anything previously experienced in the Mediterranean theatre. On the night of July 10, 1943, as Allied forces landed on Sicily's southern coast, the Luftwaffe mounted a maximum effort attack against the invasion fleet. Approximately 150 German and Italian aircraft attempted to bomb the transports and landing craft concentrated off the beaches. The night was dark, with scattered clouds and no moon. Traditional anti-aircraft doctrine would have relied primarily on barrage fire and searchlights. The SCR 584 equipped batteries operated differently. Each radar acquired and tracked individual aircraft, directing guns to fire predicted barrages that intercepted bombers before they reached attack positions. The night sky erupted with shell bursts that appeared with geometric precision, as if invisible hands were placing them directly in the paths of aircraft the gun crews never saw. Luftwaffe losses that night exceeded 20 aircraft, an unsustainable casualty rate for the diminishing German forces in the Mediterranean. Italian losses were even higher, as their aircraft lacked the performance characteristics to evade radar-directed fire effectively. The attacks achieved minimal results, with most bombs falling harmlessly into the sea or hitting empty beaches. The 1,000 Allied ships supporting the invasion suffered negligible damage from air attack. German post-mission analysis struggled to explain the defensive effectiveness. The number of Allied anti-aircraft guns had not increased dramatically from previous operations. The gun types remained standard Allied weapons. Yet the hit rate had increased by a factor that made conventional explanations inadequate. The reports from surviving pilots described fire control accuracy that seemed impossible without some revolutionary advancement in radar technology. General Martini's signals intelligence staff intensified efforts to characterize the new Allied radar. Aircraft were sent on deliberate reconnaissance missions, carrying receiver equipment designed to detect and record electromagnetic emissions. These flights occasionally detected strong pulses of microwave energy from coastal defense positions, but the brief duration and high frequency made detailed analysis difficult. What German intelligence did not yet understand was that they were attempting to characterize not just a radar, but an integrated fire control system that represented American mass production and systems engineering at their most effective. The SCR 584 was not merely better than German systems, it was fundamentally different in concept, execution, and operational doctrine. The Italian campaign that followed Sicily's conquest provided additional opportunities for SCR 584 deployment. As Allied forces fought up the Italian peninsula through late 1943 and into 1944, the radar-directed anti-aircraft batteries protected ports, airfields, and troop concentrations from Luftwaffe attack. The German Air Force, already stretched thin across multiple fronts, could not sustain the loss rates imposed by radar-directed anti-aircraft fire. Salerno, Anzio, and Naples all received SCR 584 coverage. The protection these systems provided allowed Allied logistics to flow relatively unimpeded, despite Germany's theoretical capability to interdict supply lines with air attack. Ports that should have been highly vulnerable to night bombing operated with minimal disruption. Ammunition dumps and fuel storage facilities, normally priority targets, suffered few losses to air attack because approaching aircraft were engaged and destroyed before reaching attack positions. The statistics from the Italian campaign told an unambiguous story. During the 6 months following the Sicily invasion, Allied anti-aircraft batteries equipped with SCR 584 systems achieved documented kills at a rate approximately 15 times higher than batteries using visual fire control methods. More significantly, the radar-equipped batteries prevented attacks that would have otherwise succeeded, forcing German aircraft to jettison bombs short of targets or abandon attack runs entirely. But the true test of SCR 584 capabilities would come not in the Mediterranean theatre, where the Luftwaffe was already weakened, but in Western Europe during the preparations for D-Day and the subsequent defense against Germany's most advanced aerial weapons. The winter of 1943 to 1944 saw intensive deployment of radar-directed anti-aircraft systems throughout southern England. The British, having observed American systems in North Africa and Italy, requested immediate delivery of SCR 584 radars for the defence of London and southeastern England. British Anti-Aircraft Command, under General Pyle's continuing leadership, had been fighting German air attacks since 1940. They understood defensive limitations intimately and recognized revolutionary capability when they saw it. American production delivered. By early 1944, over 200 SCR 584 systems had been deployed in the United Kingdom, primarily concentrated around London, ports on the southern coast, and the airfields from which the strategic bombing campaign against Germany was launched. Each system represented 4 tons of sophisticated electronics, precision mechanics, and computational capability that Germany could not match. The timing proved providential. In June 1944, Germany launched its V-1 flying bomb campaign against London. These unmanned aircraft, essentially cruise missiles propelled by pulse jet engines, represented Germany's attempt to continue the strategic bombing of Britain without risking increasingly scarce aircraft and trained aircrew. The V-1 flew at approximately 400 miles per hour at altitudes between 2,000 and 3,000 feet. Traditional anti-aircraft doctrine struggled with the V-1 threat. The flying bombs approached at high speed and low altitude, providing minimal engagement time. Visual tracking was difficult because the small target offered little contrast against ground clutter. Searchlights were ineffective because the V-1 had no crew to blind or disorient. The only solution was to shoot them down, but hit rates using visual fire control methods remained discouragingly low. The SCR 584 transformed V-1 defense. The radar could detect the incoming flying bombs at ranges exceeding 20 miles. The automatic tracking followed the V-1's steady course with perfect precision. The M9 director calculated firing solutions that accounted for the target's high speed and low altitude. The guns engaged with predicted barrages that intercepted Vohn's second while they were still miles from London. Statistics from August 1944, at the peak of the V-1 campaign, demonstrated the radar's effectiveness. Of approximately 300 Vohn's second launched toward London during the first week of August, anti-aircraft guns destroyed 97. Of these 97 kills, 82 were achieved by batteries equipped with SCR 584 systems, despite these batteries representing less than one-third of the total anti-aircraft guns deployed. The hit rate for radar-directed batteries averaged 1 kill per 40 rounds fired. This represented effectiveness more than 50 times better than the historical average for anti-aircraft fire. More critically, the radar-equipped batteries achieved kills at ranges up to 6 miles, well before Vohn's second could threaten London proper. The flying bombs that survived the anti-aircraft barrage faced fighter interception, with only a small fraction reaching the city. By September 1944, the V-1 campaign had effectively failed. The combination of SCR 584 directed anti-aircraft fire, fighter interception, and the Allied advance overrunning V-1 launch sites in France reduced the threat to minimal levels. Of the approximately 10,000 Vohn's second launched at Britain during the entire campaign, fewer than 2,500 reached London. The remainder were destroyed by anti-aircraft guns, primarily those equipped with American radar, or shot down by fighters. German technical intelligence obtained fragments of SCR 584 equipment from crashed Allied aircraft and captured positions during late 1944. The examination revealed sophisticated construction that exceeded German radar manufacturing capabilities. The microwave components, the servo mechanisms, the electrical design, all demonstrated engineering excellence and manufacturing precision that Germany could not replicate given resource constraints and Allied bombing of industrial facilities. Oberst Josef Kammhuber, who commanded German night fighter forces and understood radar technology intimately, reviewed captured SCR 584 components in late 1944. His assessment, preserved in Luftwaffe technical reports, acknowledged that the American system represented a generation of advancement beyond German fire control radars. The automatic tracking, the computational fire control, the integration of all elements into a mobile system, these achievements exceeded what German industry could produce even under ideal circumstances. The psychological impact of technological inferiority manifested throughout the Luftwaffe during the final year of the war. Pilots knew that Allied anti-aircraft defenses could track them through any weather, day or night, and engage with accuracy that made every mission increasingly hazardous. The days when darkness or clouds provided sanctuary had ended. The electromagnetic spectrum had become transparent to Allied sensors, and German aircraft were visible regardless of visual conditions. Training doctrine had to be revised. New pilots were taught that evasive maneuvers must be more radical and more frequent than previously required. Attack approaches must be at extreme low level or high altitude, avoiding the medium altitude envelope where radar-directed guns were most effective. Mission planning assumed significantly higher loss rates and reduced operational effectiveness. The Luftwaffe was adapting to technological inferiority it could not overcome. The final campaigns of the war in Europe saw SCR 584 systems deployed across the advancing Allied front. As American and British forces pushed into Germany during 1945, the radar-directed anti-aircraft batteries protected bridges, supply depots, and troop concentrations from Luftwaffe attacks that were increasingly desperate and ineffective. German pilots, many of them teenagers with minimal training, flew obsolescent aircraft against defences they could neither see nor evade. The Rhine crossings in March 1945 provided the last major demonstration of SCR 584 capabilities in Europe. The bridges at Remagen and the crossing sites at Oppenheim were defended by multiple radar-directed anti-aircraft batteries. German attempts to destroy these bridges with air attacks failed completely. Every approaching aircraft was tracked from the moment it came within radar range. Predicted barrages intercepted bombers before they could line up attack runs. The few aircraft that penetrated to attack range faced such intense, accurate fire that bombing effectiveness was minimal. Statistics from the Rhine crossing operations showed that anti-aircraft batteries equipped with SCR 584 achieved kill rates exceeding one aircraft destroyed per 50 rounds fired. The bridges remained operational throughout critical periods, when German demolition of crossing sites would have significantly delayed the Allied advance. The failure to destroy these bridges, due in large part to the effectiveness of radar-directed anti-aircraft defense, accelerated the collapse of German resistance in the West. The Pacific theater saw parallel deployment of SCR 584 systems, though the tactical environment differed significantly from Europe. Japanese aircraft doctrine emphasized surprise attack and kamikaze tactics that valued pilot sacrifice for mission achievement. The radar-directed anti-aircraft systems provided American forces with defensive capabilities that devastated Japanese air attacks during the final campaigns. Okinawa, in April through June 1945, became the ultimate proving ground for radar-directed anti-aircraft defense. The island was defended by the largest concentration of anti-aircraft guns ever assembled by American forces, including dozens of SCR 584 directed batteries. Japanese forces mounted sustained kamikaze attacks, with over 1,500 aircraft attempting to crash into American ships supporting the invasion. The radar-directed guns destroyed hundreds of attacking aircraft before they could reach the fleet. The M9 directors calculated firing solutions for targets approaching at high speed, often in clouds or rain that would have prevented visual engagement. The 90mm and 5-inch guns fired in continuous predicted barrages, creating zones of destruction that Japanese pilots could not penetrate without being hit. Despite the intensity of Japanese attacks, which continued for nearly 3 months, the radar-directed defenses prevented catastrophic losses to the fleet. While many ships were damaged and some were sunk by kamikaze hits, the majority of attacking aircraft were destroyed before reaching targets. Post-battle analysis indicated that SCR 584 equipped batteries achieved kill rates more than 20 times higher than batteries relying on visual fire control. The final accounting of SCR 584 impact extended beyond mere statistics of aircraft destroyed or missions prevented. The system had fundamentally transformed the relationship between offense and defense in air warfare. Before microwave radar and automatic fire control, aircraft could operate with reasonable confidence that anti-aircraft defenses were primarily effective only under ideal visual conditions. Darkness, weather, and altitude provided sanctuary. The SCR 584 eliminated sanctuary. Aircraft became visible through electromagnetic detection regardless of visual conditions. Tracking became automatic and continuous regardless of evasive maneuvers. Fire control became a matter of ballistic calculation rather than human judgment. The result was defensive effectiveness that exceeded what had been considered possible just 3 years earlier. Over 1,400 SCR 584 systems were produced during the war. These systems, deployed across every theatre where Allied forces operated, created an electromagnetic shield that protected ports, airfields, troop concentrations, and naval forces from air attack. The psychological impact on Axis air crews, who understood they were visible and vulnerable regardless of tactical conditions, accelerated the collapse of effective air operations during the war's final year. The technological superiority represented by the SCR 584 extended beyond the immediate military applications. The servo mechanisms developed for automatic tracking became the foundation for post-war control systems, used in everything from machine tools to spacecraft. The analog computing techniques pioneered in the M9 Director influenced computer development through the 1950s. The microwave radar components evolved into communication systems, weather radar, and eventually air traffic control systems used worldwide. Dr. Ivan Getting, who led the SCR 584 development program, would later apply similar principles to navigation systems, eventually leading the development of GPS satellite navigation. The systems engineering approach used to integrate radar, computers, and gun control into a unified system became the model for complex military systems developed during the Cold War. The production expertise gained manufacturing 1,400 sophisticated radar systems enabled the electronics industry expansion of the post-war decades. But the immediate historical significance lay in the system's wartime contribution. At critical moments, during the Sicily invasion, the V1 campaign, the Rhine crossings, and Okinawa, the SCR 584's capabilities prevented Axis air forces from achieving objectives that might have prolonged the war or increased Allied casualties. The electromagnetic spectrum had become a battlefield where American technological superiority proved decisive. The German examinations of captured SCR 584 components revealed sophisticated engineering, but could not duplicate the system's capabilities. By the time German technical intelligence fully understood what the Americans had achieved, Germany lacked the industrial capacity, the materials, and the time to develop competing systems. The war would be over before German radar technology could close the gap that had opened in 1943. Luftwaffe officers who survived the war and participated in post-war technical assessments consistently acknowledged that Allied radar superiority, particularly in fire control applications, had fundamentally undermined German air operations' effectiveness. They had fought courageously against technological advantages they could neither match nor counter. The darkness that should have protected them had become transparent to electromagnetic sensors they could not see or deceive. The men who designed, manufactured, deployed, and operated the SCR 584 systems transformed defensive anti-aircraft warfare from an uncertain art requiring ideal conditions into a reliable science that functioned regardless of visibility or weather. They created weapons that could see through clouds and darkness, track evading targets with mechanical precision, and direct gunfire with accuracy that seemed impossible using previous technology. The British officers who had fought through the Blitz with inadequate fire control systems, the American gunners who learned to trust radar rather than their eyes, the engineers who solved countless technical problems to make automatic tracking work reliably, all contributed to a technological revolution that changed aerial warfare fundamentally and permanently. In the end, those who could see electromagnetically won, and those who remained visible only optically faced defeat in a dimension of warfare they entered without adequate preparation. The SCR 584 had made the invisible visible and the untouchable vulnerable, turning the sky from sanctuary into killing ground for those who lacked equivalent technology. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.